Hello everyone, welcome back again to the course Comprehensive Slope Stability Analysis using PLAXIS 2D. This is tutorial number 21, Drainage Conditions in PLAXIS 2D, Drained versus Undrained A, B, and C. So as we know and from previous lectures, when we define the material using a specific constitutive model such as a Mohr column, so in a Mohr column we have a drainage type under the soil model. When we expand, as we can see, we have drained, undrained A, undrained B, undrained C, and also we have a non-porous. So in this lecture, the purpose of this lecture is to explain the difference between drained condition and undrained condition in soil behavior in PLAXIS 2D, and I will shortly explain what is the difference between a drained condition and these three undrained conditions A, B, and C, and also we have a special case, non-porous. So in this lecture you will understand what is the difference between these drainage type, and also at what specific condition we should select or use each of these drainage type. So first of all, we have a drained condition. In this condition, the stiffness and the strength of the soil are given in effective stress parameter. For example, if I open the PLAXIS, in here we have PLAXIS 2D. So I will open the PLAXIS, it will be more clear. And we click OK. In here we have a material. If I click on show material, for example, when we define a new material, for example, if I type a soil, in here we have a Mohr column. So under the Mohr column we have drained, undrained, B, C, and also non-porous. If I select undrained in mechanical properties, we can see the stiffness parameter, elasticity, and Poisson ratio is given or in term of effective stress, and also the shear strength parameter, cohesion, and internal friction angle is they should be in term of effective stress. So in this condition, in drained condition, it means this, the soil has enough time for water to move out of pores, and it means no excess pore water pressure will build up when we use a drained condition. If we take a simple example, imagine we have a sand or gravel, and since the sand or gravel have a lot of large pores, so they can drain water very quickly, and pore pressure doesn't trap inside these types of material. And when we should use this condition, when we have a permeable soil like sand or gravel, and we want to consider the long-term condition, and or when we have slow loading and steady seepage. So it means when we use a drained condition, we define the stiffness and strength of the soil in terms of effective stress parameter, and no excess pore water pressure is created or generated inside the soil. The second case, we have undrained condition A. In this condition, soil is impermeable, or it means loading is so fast and the permeability is very low, so the water cannot drain. In this undrained A, also both stiffness and strength are given in effective stress parameter, but PLAXIS automatically accounts for water incompressibility and generates excess pore water pressure. This case is almost similar to the drained condition, in terms of defining the stiffness and strength parameter, except that in this undrained condition, the excess pore water pressure is generated. For example, when we have a clay foundation and it's loaded by very quickly by a structure, and clay cannot drain immediately because the permeability of the clay is low if you compare to the permeability of sand or gravel. So in this situation, pore pressure builds up. So in PLAXIS, if I select Undrained A, again we can see we have elasticity and Poisson ratio and shear strength parameter in terms of effective stress. Also, we have number 3, undrained condition B. This undrained B is similar to A, but here stiffness is given in effective stress, while the strength is given in undrained shear strength instead of effective cohesion and internal friction angle, and pore pressure are still generated. So the only difference between undrained B and undrained A is that the shear strength parameter of the soil is given in undrained shear strength. If I open the PLAXIS and if we select undrained B and click on mechanical, so we can see again the stiffness parameter is given in terms of effective stress. But in shear strength, we can see the internal friction angle and the latency angle. We cannot set or give any value. That's why the soil is defined in terms of undrained shear strength. As an example, if a triaxial test on soft clay, and when the only data we have from the laboratory is undrained shear strength, so we can use this case instead of undrained A. And when to use, as I mentioned right now, when we only have undrained shear strength data from lab, but still we want to account for pore water pressure development in the soil. Number 4, we have undrained C. In this undrained condition, the stiffness parameter and strength parameter both are defined using undrained terms. For example, if I select undrained C, in here you can see it's undrained Poisson ratio and undrained elasticity, and also the shear strength parameter is undrained shear strength. So in this condition, both of them are defined using undrained terms. But in undrained C, no pore pressures are generated inside the analysis, and effective stresses are then back calculated. So it means in undrained C, there is no pore pressure development inside the soil. So for example, this is called a total stress analysis, because these are these three drained and undrained conditions are based on effective stress analysis, while number 4, undrained C, is based on total stress analysis. And all geotechnical design codes often provided only undrained shear strength without pore pressure data. And when to use when we want to perform a total stress analysis, and if we don't need to take pore pressure. And actually this method is simple and more conservative than the other method. Also, we have another drain condition. We have a non-porous material, and this condition, soil is treated as if it has no pores. Consider when we have a solid rock or solid concrete material, so the water cannot goes inside the pores because there is no pores inside the material. And for example, as I mentioned now, when we have a massive rock slope or concrete block inside the soil, we can model it as a non-porous material. So imagine when we have a concrete retaining wall or concrete foundation using a volume element. In this situation, we can use it as a non-porous in a term of drainage condition. And these material, of course, are impermeable material like rocks or structural element. So as a conclusion and summary, for drained condition used for sand or gravels in long-term condition, so no pore pressure is generated. For undrained A, for example, used in clay with effective parameters, effective cohesion and effective internal friction angle, and pore pressure is considered. And for undrained B, it's used in clay with undrained shear strength. So also pore pressure is considered. The difference between undrained B and undrained A is that undrained A, the stiffness parameters and shear strength parameters are used in terms of effective parameter, while in undrained B, stiffness parameters still are used in terms of effective, but the shear strength parameters used in terms of undrained shear strength. For undrained C, as I mentioned before, it's a total stress analysis and pore pressure is ignored in this undrained condition. And regarding the non-porous, so it's used in a rock or rigid bodies like concrete or rigid material, so there is no pores and no pore pressure is generated. So this was for this lecture. I hope it was clear and useful. Thank you for watching. See you in the next tutorial.